All right, welcome. This is the third and final lecture for Ralston Valley High School AP Chemistry's lecture series in Chapter 17, in which we're investigating electrochemistry. Specifically, we will discuss today electrolysis. Let's move on to our first slide. All right, over the last couple of lectures, we've primarily been focused on an understanding of galvanic cells. Those are cells in which the forward process is spontaneous that do not require outside intervention for the reaction to occur within the redox system. In this particular conversation, we're going to be focusing on the reverse process of a galvanic cell, which is what we refer to as electrolysis. By definition, electrolysis is a process in which current is forced through the cell in order to induce a chemical change to occur, in which the cell potential of the operating cell would be a negative standard cell potential. Now, an electrolytic cell, therefore, by definition, would be a cell which uses electrical energy to produce a chemical change. So whereas galvanic cells would be cells that could be used to do useful work, an electrolytic cell would be a cell that consumes energy in order to cause a chemical change to take place. Now, the degree to which that chemical change will actually occur is going to be dependent upon a number of different factors. First of which, the amount of current which moves through the system, measured in units of amperes, or commonly, you may recall from your physics days, amps. The current in a chemical equation is given the symbol I, and the unit of an amp is given the capital letter A. By definition, the flow of current I is defined as the charge Q per given unit of time T. And by definition again, 1 amp of current is equivalent to 1 coulomb of charge moving through a circuit per second. So again, amps are equivalent to coulombs per second. So again, the first factor which is going to determine the degree to which a chemical change occurs within our cell is how large that flow of current is. The second factor which will determine how that chemical change occurs within the cell is how long the reaction runs for. And this process by which we are able to cause chemical change to occur by applying electrical current, as it turns out, has a lot of useful applications in the real world. One of the primary ones is a process we refer to as electroplating. Electroplating is a process by which we're able to deposit a metal onto the surface of an electrode by a reduction of a metallic ion within a solution. And there's a lot of places in the real world where this process is very useful. Among them would be things like chrome plating car parts to help resist corrosion and give them a nice shiny sheen that makes the cars attractive. You also might see electroplating used in the process of producing galvanized nails or screws for use in outdoor applications like, say, roofing or decking. In that process of producing a galvanized nail or screw, we end up depositing zinc ions onto the surface of a nail or a screw to form a thin coating of zinc metal around the outside. And that thin coating of zinc metal then further oxidizes to produce a coating of either zinc oxide or even zinc carbonate, which itself is a very, very highly insoluble substance and more or less impermeable to water, which then protects the core of the nail or screw, generally composed of iron, from further oxidation via the rusting process. So let's go ahead and see on our next slide here a pathway we tend to follow for these electrolysis problems that you're going to be facing on the AP test. All right, now in comparison to the previous problems we've been working with in the last couple chapters, these electrolysis problems are relatively straightforward and friendly. There's a variety of different factors that might be useful to us in a calculation involving an electrolytic cell. Among those, number one, first of all, is the current that is currently being applied to the system, again, measured in units of amps, which are, by definition, the number of coulombs of charge moving through the circuit per second. Also useful here is to remember we gave you a factor of the defined value of the Faraday, which was the charge on a mole of electrons, that is 96,485 coulombs per mole of electrons. And also useful to us here is an understanding of the number of moles of electrons required per mole of the metal, which we say is plated out or reduced, forming a solid on the surface of our electrode. Now, looking at these three factors here, notice that all three of these factors are compound units. That is, current in amps are coulombs per second. Faraday's are coulombs per per mole of electrons, and moles of electrons per mole of metal are all essentially ratios. And as such, they can all be used as conversion factors within a monorail. So these electrolysis problems usually boil down to nothing more than solving a monorail using dimensional analysis. Now, the sequence of steps we generally follow for an electrolysis problem are as follows. You'll be given primarily an amount of current which is flowing through the system, and as well as the time over which the reaction is occurring. Using both the current and the time, your sequence of steps will then take you to calculate the quantity of charge which is moved through your system. From that, you can then determine the number of moles of electrons which must have moved, which would then in turn allow you to calculate the number of moles of metal which have been plated out. And from that number of moles, you can then do a quick, easy calculation to find the number of grams of metal. Now, likewise, this entire process can also be run backwards. That is, on the test, they might instead give you a mass of metal that needs to be plated out, and then from that mass of metal, you could calculate the number of moles of metal represented, and then from that, the number of moles of electrons required to plate out that number of moles of metal. And then from that number of moles of electrons, the quantity of charge in coulombs represented by that number of electrons, and then that would tell you essentially what amount of current would have to be run or how long the reaction would have to run for the electrolytic cell to generate the desired amount of metal given to you in the problem. So with this kind of flowchart pathway here, let's go ahead and take a look on our final slide here at a couple of examples where we'll see this in action. All right, we've got two example problems we're going to work here relating to electrolytic cells. The first of which is going to ask us here what mass of copper will be plated out when 10.0 amp current is applied across a solution of copper 2 sulfate for 30 minutes. And recognize here, the first thing I want to do is take a look at the reduction which is likely to occur within this system. Again, we are using a solution here of copper 2 sulfate, and the copper 2 sulfate contains dissolved within it copper 2 ions, Cu2 positive, which require 2 electrons to completely reduce the copper to solid elemental copper over the surface of our electrode. So the equation here, Cu2 positive plus 2 electrons forms elemental copper, is the reduction that's going to be occurring within our system. And I'm going to go ahead and recognize that as an electrolytic cell problem here, I'm going to set up a monorail. Starting off with this monorail here, I've got two given values, the first of which is the 10.0 amp current, and then secondly, I've got the 30.0 minutes of time that we're applying this current for. Now, recall from our definition of current is by definition the flow of charge per unit of time, that is coulombs per second. And as such, that is a ratio, fundamentally a conversion factor. So I don't want to start my monorail with that conversion factor, so I'm instead going to start here with the 30 minutes of time that has elapsed. And starting with 30 minutes here, the first conversion I'm going to make is per 1 minute of time passed, there are 60 seconds. And I need to get into seconds here because, again, by definition, an amp is coulombs per second. So for my third conversion along the way here, I'm going to state that there are 10.0 coulombs of charge passing through the system every 1 second. And note again that ratio of 10 coulombs per second is the amperage of this system. All right, so now I'm currently in units of coulombs. Next step, the Faraday by definition is the amount of coulombs per mole of electrons, and that is there are 96,485 coulombs of charge per mole of electrons. And then next step here from my reduction reaction, I noted that it required 2 moles of electrons to completely reduce 1 mole of copper from copper 2 ions into elemental copper. And then final step here, now that I've got moles of copper, per 1 mole of copper, looking up on my periodic table, there are 63.546 grams of copper. And with this setup here, note that my units cancel out nicely here. Minutes cancel with minutes, seconds cancel with seconds, coulombs of charge cancel, moles of electrons cancel, and moles of copper cancel, leaving me with units of grams of copper metal plated out. And plugging these values into my calculator, I find a value of 5.93 grams of copper can be plated out onto the surface of that electrode over those 30 minutes of running the 10 amp current through our copper 2 sulfate solution. All right, so first example problem done. Let's now take a look at a second example, which is the same idea, but now kind of running in reverse. In example number 2, we're going to ask you here, how long must a current of 5 amps run through a solution of silver nitrate in order to yield 10.5 grams of plated silver on the surface of our electrode? So yet again, I'd like to start by looking at the reduction which is going to be occurring within our system as this electrolysis reaction runs. The silver ion's charge within the solution of silver nitrate is only +1, meaning therefore it only requires 1 electron to reduce the silver ion into elemental silver metal. So I've got Ag positive plus 1 electron forms Ag elemental. All right, yet again, I'm going to need to set up another monorail. And again, with 2 given values in this problem, again, a 5.00 amp current and a mass of desired silver of 10.5 grams, I'm going to yet again recognize that amps by definition are coulombs per second, and as such are a conversion factor. So I'm instead going to start now with my 10.5 grams of silver that we want to plate out in our system. And converting now, I'll go from grams into moles. Looking up on my periodic table, there are 107.8682 grams of silver per mole of silver atoms. And now from my balanced equation, to produce 1 mole of solid silver would require 1 mole of electrons to be transferred to completely reduce that 1 mole of silver ions. And with 1 mole of electrons, I can now convert that into coulombs of charge. There are 96,485 coulombs of charge per mole of electrons. And then final step along the way here, I'm now going to use my current to convert from coulombs of charge into time. By definition, a 5 amp current means that 5 coulombs of charge are running through our system for every 1 second of time which passes. So I've got my monorail set up, and now note here, I can go ahead and cancel out units. Grams of silver cancels with grams of silver. Moles of silver cancel as well. Moles of electrons cancel, coulombs cancel, leaving me with units of time in seconds. And I can multiply across my numerator and divide by the denominator there. Solving this monorail here gives me a value of 1,880 seconds to 3 significant figures. So that means, therefore, if I ran this cell at a operating amperage of 5.00 amps for a time of 1,880 seconds, I could expect to see 10.5 grams of silver metal plated out onto the surface of the electrode within the system. All right, that is it for electrolysis. We have now completed the entirety of our discussions around Chapter 17 for electrochemistry. Thanks for listening. We'll see you at the next lecture.